Right, welcome everybody to the British Astronomical Association GNU Radio for Radio Astronomy meeting tonight, the 31st of January 2026. We don't seem to have too many people taking part, but I suppose it is a rather niche area. But I know there are quite a few other people who do log on and look at the videos, so and a number of people as well who have also apologised tonight for not being able to attend. So perhaps a bit short anyway. But nevertheless, for those of us that are here and for those that log in online, I think you'll find this quite exciting because we're going to a little bit later on review the homework exercises that we decided on at the last meeting. But in addition, we're going to start off this evening with Ted Klein presenting a new version of part of his easy radio astronomy software that he's been writing for GNU Radio. This is not meant to make people feel depressed because this is working so well. I'm trying instead to motivate everybody to think, gosh, this is where eventually we can get to with a bit of effort and practice. So we were briefly just talking about this before we started the meeting tonight, and Dave, you came up with a brilliant question, which I've got to say I was thinking myself, and perhaps that would be a good introduction if you could ask that to Ted, and then he could, in answering that, perhaps go on and explain to us what it is that he's doing on his beta software.
Okay, yeah, sure. Okay, so I've been using Ezra for, well, not that long really, just I don't know, 4 or 5 months, I suppose, and it's absolutely blowing me away with its what it can do. Absolutely incredible piece of software. I absolutely love using it. Really, really good. Ted's support for it is, I've never encountered anything so well supported, so well done before in anything I've done in my life. Anyway, so I love Ezra. Fantastic. I've seen on Andy's website a tantalising glimpse of GNU Radio being used to do something similar. And I think probably Ted's going to talk about that later on. But the question raised in my mind, I thought, well, okay, what's the problem? What problem we're trying to solve here? Ezra was so good. What is it that GNU Radio could do that enhances it? That maybe Ezra can't do at the moment or could do. But what is it that GNU Radio will bring to the table?
Ted, pass it over to you.
My turn?
Yes, it's your turn.
And now it's my turn? Oh, my. Okay. Well, thank you, Dave, for all the kind comments.
But basically, Ted, what's the point?
All we're trying to do is collect data from the radio sky, right? Write down lots and lots of numbers having to do with power values for different frequencies. The frequencies are in little channels, so we call them frequency bins, like a bucket frequency bins, and if you get a whole bunch of them, the default and easy in Ezra right now is 256 of them, then you get kind of a bumpy spectrum, and that's kind of neat. And if you can keep writing that down, you are collecting data. If you collect other data right next to it, called reference samples, then you get to analyze it a little bit better. And that's the whole general idea of Ezra. Other folks have been collecting data as well. Despera from West Virginia has a program to collect data, and they chose to use the engine called GNU Radio. That allowed them to use different SDRs and things like that, and it saved them some trouble. It's a little mysterious, and so Ezra chose to use Python, which might be understandable by more folks, is what I was hoping. And I post all the source, so you can go look and see how I do it. It's a little convoluted because I keep adding stuff to it, making it fatter. But in theory, you can look at it and play with the source and do it yourself as well, make changes. The whole idea of open source. So I used Python, and I simplified things by only talking to the least expensive radio, the RTL SDR version of an software-defined radio. Okay, and so I have posted that, and I support that, and folks can ask me questions about that, and I'm willing to talk to them about it and try to get them to go. It's been helpful, but I want to collect data even faster. I want to collect data even from all kinds of SDRs. And so let's try to break out of this Ezra box and do even more. We tried some experiments with SOAPy drivers. I'm not sure we can do that on Windows. I think we can now. The world has kind of progressed since the time when we started. So that's a possibility to do it all in Python. But gosh, if we could get GNU radio to work, then we're using multiple cores on our computers. And that's a step up from Python, I think. And we're running a lot of our program in assembled and compiled C code, which might be even faster. Again, faster and faster samples, more samples per second. So instead of Python, could we at least collect the data using GNU radio? Whew. Okay, that's the introduction there. And so we're making some progress on it, and Brave Andy here is trying some of my things. Let me share a picture and show you kind of where we're beginning. I guess share, and now we do window and find the right window. Yeah, I think this, the click doesn't work. All right, there we go. I'm hoping that you're seeing this guy now.
Yep, flow chart come up now.
Andy has a more complicated program, but he started with this one. Let me walk through it slightly for you, Dave, and anyone listening on the recorded message, on the recorded program. There are a bunch of variables across the top. Some of them are, the top two on the left, you get maybe the first and the third one, I guess. I've changed the order. First and the third one, you get with every program, the sample rate and some other options up here that just record stuff. I use the options kind of to record what version I'm working on, because I keep coming up with new and better versions all the time, and that has to be indicated someplace. Down below, there are not many boxes in here, actually. Over on the left, maybe you see my cursor, there is a radio block to talk to the actual hardware. It's spitting out a whole bunch of readings along this wire that are a stream of numbers. They get turned into a vector, so now they're collected as 256 units of frequency power measure. Well, not even that. These are actually voltages. And then it goes into the FFT, which makes them into essentially then down into this third box on the bottom. And now I think we actually have packets of 256 power measurements. So we think of that as a spectrum for the power for several different frequencies. But there are a lot of them. We're talking, 20,000 of them or so to make, actually much more, maybe 100,000 of those to actually average, I'll say, integrate is the fancier word, into things we actually want to write to a file. Somebody has to collect those. Somebody has to average all those samples, so many of them, whatever number you pick, or integrate them, in the fancy word, into one sample to be written to the file and actually write it to the file. And so this big tall box over here is what I've come up with. I think if I zoom in, we could see it better. I'm hoping that's a little more visible. Wow, look at all the lines inside it. It has all kinds of parameters to pass to it. Some of them are passed, some of those values are passed by variables, and some are just typed in. For example, the name of my observatory is called Big Dish H here, and I just typed that into this box. The location of where that antenna is on the Earth is written in here with 3 numbers, and I've just typed that in. Sure enough, you could put a variable and have that more visible to the operator of this program. But that's a complication I was trying to avoid in my introductory thing here. If we double click on it, let me not go there yet. So this big box does a lot of stuff. It also squirts out on this orange pin the spectrum that it is writing to the file. Maybe I want to see what it looks like. And so I'm squirting it out to a graphical user interface display, which shows that spectrum that I'm writing out. All right. There's another output over here in gray. That's called a message, and that's more part of the program process. It comes out and gets written to a box that has the word freak in here, so frequency, and then that talks to the box below it, which is the official definition of the frequency, and that changes the value of the variable called frequency. So my big box can change the frequency. And then way over here on the left, this SDR interface box that actually talks to the SDR uses that value called frequency. We look inside. We have changed the last one down here to be FERQ for frequency. And so I am changing the frequency of the receiver. Woo! That took some work to do, but that's what's going on here. If my box over here, my big box on the left, can change the frequency, then perhaps we can record samples from the sky. Ezra calls those antenna samples. And this big box could also change the frequency to receive, well, samples from the sky, but not at the galactic hydrogen frequency. We don't expect to see any hydrogen in these samples, and we call that a reference sample. And that helps the analysis later. This is becoming a long tirade, I apologize, but this is much of it. For those who are still listening, if we double click on this box in the middle, we can see that there are a lot of variables. It goes on forever. Some have numbers written in them. Let's see, can I zoom in or anything like that? No, I'm sorry, on the video, they're just going to be small letters. Some of these things are just written in as numbers. Here's the big dish written in as a string.
So, sorry, at the moment, Ted, we're not seeing the what came up.
Me. Yeah. Because I have to share another window if I pop that up. Let's see, if I do this, and if I, pardon me, yeah. Do this, and then we come back to you, and we actually share it. Let's look inside that box too. Window, and where's that little guy?
So while Ted's doing that, Dave, your homework for next time is to write your own Ezra Sync Python block to achieve all the same outputs.
Oh, that would be painful.
But you can do it in C++ if you prefer.
I see. Well, maybe, I don't know. I'm not sure I can normally share it. We're on the edge of science here.
I don't know if you
I
feel
share,
like sharing your whole screen, but if you do that, you'll definitely share it.
yeah, all right. We're learning in front of you. If I share this program box, I don't think you see the properties, correct?
No,
The smaller box?
no.
Yeah. All right, so we're fighting between teams and... Oh, wow. Yeah, I guess. I'm trying. Oh, God. So many choices. There's a choice of one, and I have to choose it, it says. Okay. Okay, now...
There it is. It's appeared now.
Pardon me for all the complications. I'm learning in front of you. This is the properties of that fat box underneath it. Can I even make it big? Oh, yeah. See all the different numbers in it. I think if I hide this, that's better. It's got lots of values all the way down here. You may not be able to read it, but sure enough, there must be lots of settings inside this box.
Can I ask you a question?
I'll take another time to explain all these things.
Yes.
But I do want to point out...
Yeah. So before you do that, Ted, can I just ask, where are the prefixes on there, or the ob's name? It says Big Dish or Big Dish 8. Is that single quotes you have around it, or double quotes?
I have chosen to use single quotes.
Okay, because that
Python,
clearly works.
That's what the Python guys seem to prefer. Although apparently double quotes can be used, and mostly I think of double quotes are helpful if you want a string that has single quotes inside it. Yeah.
Right. So it's worth saying that for people who are watching the video, or for Dave, that something I've discovered in the last few days is that if you put it in quotes like that, then it treats it as an actual value. But if you take the quotes off and say I just had Big Dish there without the quotes on the prefix, then it would treat it as a variable. So you could actually have another variable entry box, which would allow you to then live, as it were, to be able to put in, or even just within the flowchart, to change that actual name, which would then be drawn into this Ezra.
So here we are learning how to deal with GNU Radio. Yeah.
Yeah. And to remind people as well, the other thing that keeps going back to haunt me, is in your integ quantity at the top, integ QTY, you've got 200 E3, and it's just to remind people that in some of the blocks you seem to be able to put in E3 like that. In some of them you can't. You have to put in the whole number, and it seems to also depend on whether you're using float numbers or integral numbers or whatever. So just bear that in mind. If it seems to register an error, you might have to change it over to just write the whole number out. Clearly not in this case on your written one there, but in other ones sometimes I notice that happens.
I think that's because I went to the trouble inside my program here to be allowed to accept it.
All right, okay.
Ted, just to ask a very silly question, probably. So is what you're showing here, the EasyCol GR Sync, is this? This looks very similar to sections of EasyCol in the conventional Ezra system.
Yeah, that's on purpose, right?
Is what you're producing here like a sort of parallel version of EasyCol that may one day have more?
It's supposed to be an advanced version of the EasyCol that I've posted.
I see. Okay.
If we get it to work, then it might need a whole bunch of documentation to tell you how to get here and install it and everything else. And then I'll pass it out and post it and tell you how to do it to run it even faster for those that are brave.
Okay.
But this is advanced, and I'm working on the next level above that to make it go even faster too.
Okay.
So yeah, but
sounds really
great.
great.
Different ways. And
Okay,
all of
thank
it
you.
is to get faster, more samples per second, and to be able to support more hardware.
Okay, it sounds fantastic. That's okay. Yeah, brilliant. Okay.
What's kind of fun is, so if I hand you this car, you can look underneath. Well, the Americans call it the hood. You guys call it the bonnet, I think. Let's look inside the thing. Way up here in the top, with this particular box that I'm at least passed to Andy, if we click on Open in Editor, oh, Andy, we're going to hit this problem, aren't we? I'm on Windows.
I think it might be working on my version, so we can you can see it there in a minute or two.
I see nothing.
No.
All right. On Windows, we don't know how to open the top. Sorry, guys. On Linux, you can click on Open in Editor and actually look at the Python code and change it if you wish to. Good luck. It's exciting. Every character matters, kind of thing. But I distribute the code inside this block. The alternative is to create an out-of-tree module, or block, I guess the correct word is, out-of-tree block that I would send to you as a Python library that you would have to install. And I think that's a more complicated process. So on Linux, go ahead, open an editor and have a look around. You can see what's going on inside. It's just Python. What I'm working on now is, can I create this Ezra Sync, as it's called now? Can I write that in C language and make it run even faster? So I'm maybe making progress. Wow, that was a lot. And Dave, your questions are all good. I was joking. There are no dumb questions, so keep asking questions. This is good.
Thank you.
Where do we go from here? Oh, Andy. So, Andy, you have actually a working version of this thing. If I back up, my program is this big. And now Andy gets to take over and show you that he's added more boxes to make it kind of friendlier when it runs.
Okay, I'll just pull that up.
Go ahead. Anyway, yep. And,
Ted, before you do that, your version, what would the output look like of your version? Would it be just a
Andy's about to show you. No,
okay.
Andy will show you. That's fine.
Okay, thank you.
His is hooked up to a real antenna, and so we get better results, as shown right now.
Yeah. The only things that have changed on this, Dave, are I've tried to make it more user-friendly by changing some of those sort of permanently set values within Ezra and within the RTL SDR box into buttons and things that you could change in the live program. So it's a bit more like EasyCall. That was the idea. So the actual underlying Ezra sync box is the same. So this is the output that you should see. Here at the moment I've set it so that ref action is off. If we change it, so you might remember that ref action gives you 3 choices in EasyCall. This is where, if you say, all this does is show you how the samples are being collected on the screen. It doesn't actually change the underlying data. So ref div divides the sample by the reference, and ref sub subtracts the reference from the sample, and the ref div just gives you a more obvious signal in a way. So if I change that to ref sub,
and that's the idea. We're just trying to emphasize the hydrogen signal.
Yeah. There are a couple of things that don't seem to work very well live. So actually changing the frequency doesn't seem to work well when you're actually running live. So you usually have to stop and restart that. We have an option at the top that Ted's put in, but again, he had this actually appearing in his GUI. I've just made it slightly nicer with a nice button. Take reference sample reading. Now if I press that, and if you look at the words on the right where it says press take reference sample, you can see that the 0 changes to 1. Oh, there you are. We've got our first. That was not from that pressing that, but it's. You can see now we've got the ref sub has now appeared on the screen with a with an obvious hydrogen line signal there showing up. So the reason I've added this a nice button to press and then pressed it just tells you whether you actually pressed it or not. And then we can start a new data file here by pressing on here. Obviously we've got an option here to switch off writing to a file if you just want to play around with it and not create an actual data file. And you can see down the bottom that you've got your observatory name and your prefix that appears in your files. Again, I've no idea how easy those are to actually change live. Haven't tried it. And then we've got our observatory longitude and latitude and height above sea level, as well as the azimuth and the elevation and the integration quantity. If you change this within a live GUI like this, and then you stop the program and then restart it, it will go back to the defaults again, so it doesn't persist over to the next time you run it. So you might still have to change it on the actual program itself. The program itself is here, so let's just switch that thing off at the bottom. So all I've done is this bit in the middle is exactly the same. This is actually the engine. It's exactly the same as before. And some people might wonder, Ted's written this Ezra sync here in Python, and they may think, well, surely that's defeating the objective exercise. You're supposed to write it in GNU Radio. But in actual fact, it's the way that GNU Radio works. So if we look at the RTL SDR source, somebody has written that in either Python or in C++. And there's things like a UHD one, which is designed for things like the Ethos USRP B210. There are various ones for different types of SDRs and different purposes. So mainly this is an idea where you can take these various blocks that people have written and you can put them together, a bit like PixInsight, if anybody does astrophotography processing, where again people write different blocks and you can use those to create your own, as it were, processing process. Yep.
Can I ask another question?
Yep.
So if Ezra's written in Python, and as you just said, this GNU Radio under the hood is Python 2, why does this run? Why can this run faster than Ezra Python?
Well, this block here is in Python that Ted's written, but that doesn't mean that all the other blocks are in Python, and many of them are written in C++.
Okay. And that's where the speed increase is coming from.
Yeah.
Okay.
The new radio allows us a new architecture here too. Each one of those wires can be run by a different core on your computer also. So now we have multiple processes running, and we're using all of your computer instead of just like one of those cores. I think Python may have a way to do some of that too. I'm not sure. Not even threads, but processes here can be split up. And GNU Radio does all the administration of that. Hooray. I have not chosen to write my Python programs with that much complexity. I don't think I'd understand it, much less pass it on to other folks that way. But GNU Radio does, so we're using our computer even more efficiently or effectively. And so things move faster.
Okay.
Yeah. So,
sounds fantastic. Okay.
all this other stuff around the outside, the ones that are switched off are basically depreciated versions of blocks I put in, but everything else, where it's, if you notice, it's all Qt GUIs or it's variables. So it's either setting variables up or it's providing some form of graphical user interface way of displaying or changing variables. That's all they are. The underlying engine in the middle is Ted's engine, and there we are, and that's it on display there.
But it looks absolutely amazing. I think I'm.
Oh, one of the
This
things
is going to
worth
be
showing
incredible.
is that on this one we can actually see it, even though this is Windows.
Oh,
It allows us to actually
good.
see it in Notebook. But on my other computer, it won't let me see it in Notebook. Don't ask me why.
So I have to catch up to you and get some setting to work. All right. So there's my program in there. There are ways to see it. It's actually in the GRC file in English. It just doesn't have all the proper line feeds to spread it out into separate lines and spaces like this. So if you scroll down, we get to see more of the Python stuff. This is all the documentation that shows up in the doc tab. Let's go down below all this. This is GNU Radio stuff. Let's scroll down at least. There's this where we get into GNU Radio, and gosh, it's messy. But it is written in Python, so that means it's somewhat accessible. Keep going, keep going. Let's get down to the useful stuff. This is just all the stuff I had to put in to interface to GNU Radio. And now finally down in here, probably in this place, is allows us to do reference samples and flush out all the antenna readings that we don't want. But let's go below that. And we finally see where we're actually writing out to a file. You see all this overhead has to be in there in lots of ways because of GNU Radio. At some point, if you don't have a data directory, I create a new data directory right there in the middle of the screen. And down below, we're finally figuring out what file name is available with that little letter on the end, A through B through Z. And then we're finally writing out the stuff to the file down here at the bottom of the page. Keep going down. That's some printing, and then finally there, we're finally writing to the file. And then oh no, we're not even doing that. That's just the file name. Keep going, and...
Say when to stop.
Yeah, we keep going, and then, okay, about there. So FP close at the top is when we're finally finished writing out the sample. And then for ref action, it has 3 choices. So anyway, this looks more like Python down in here. But there's a lot of this file that is simply to interact with GNU Radio and answer all its questions. But it's in Python, and it's somewhat like English. We can talk about those fancy things another time, but this is an example that I have been developing. All of this is pioneering. We're learning along the way.
Okay. Well, thank you very much, Ted.
And now this is a whole lot of trouble, and I'm still not sure it's terribly worth it. If you had hardware that wasn't an RTL SDR, I would now suggest just using the SOAPy driver version that I'm providing to those who actually ask. It's not terribly supported. I'm not sure if it's working perfectly, but it's something to explore. And this is the next level using GNU Radio. And then we're trying to go even farther than that as well. Wow.
Okay, well, thank you very much indeed. Anything else you'd like to ask, Dave?
No, I was just really looking forward to seeing this when it finally appears, Ted. It looks absolutely incredible. And thank you very much for the explanations. That's that really looks really, really good.
Can I ask you a couple of questions, Ted? One thing is you were mentioning this business of messages, which is an interesting way of actually feeding back from your Ezra sync block back to the RTL source, because obviously it's going from RTL source in this direction towards here, but it's continuously running stuff down that pipeline, and you're able to feed back from the end of the pipeline back to the front by using a variable, which I found quite interesting.
Is there a question in there?
Yeah, I'm just trying to understand how it works more. So you have to define the name here, do you? Variable freak, and then
Well, let's talk about what's going on.
Okay.
Over on the left-hand side, we got something that talks to the hardware, that block called RTL SDR source.
Yep.
One of the settings, it says, so hey, what frequency do you want me to go look at? And so indeed, one of those settings down in there is at the bottom called channel 0 frequency in megahertz.
Yeah, I see it now.
We have changed that, kind of only the only thing we've changed in this block, this one setting. We've changed it from a number to a variable name called FERQ for frequency. That number is one of your variable, actually the variable block at the bottom right is where I've moved it to. That is the definition of the variable, and I've placed it over there because I am trying to change that variable from within the program. And I find that complicated, but at least I found a way. You have to use a message to variable block. You can see that in the bottom right, just above the variable. And somehow now you have to talk to that new box with a message. And so my fancy box, big fat box in the middle, Ezra Sync, has an output pin for messages, or at least the message of freak. And so finally inside my program, Ezra Sync, I can change eventually the variable that the receiver uses. It's that complicated.
So speaking simply, it's not possible to just put an arrow from here sort of somehow back up to here to feed it straight back in. You have to use this variable in between, do you?
This is the way I've chosen to do it now. We wanted a variable to change the frequency anyway.
Yeah, okay.
Indeed, on the left-hand side, there is a gray input called command, and perhaps I can send out a text string as a command to change that and maybe other things. But there's still this feedback loop that takes time in real time to occur as the computer catches up with itself. I am having trouble figuring out the correct incantation in GNU Radio Python to send out a text message. So far, I have the right incantation to send out a number message. So this is programming inside that Ezra Sync. My problem is finding examples to help me. GNU Radio is new, and much of it is not completely finished, yet we're using it anyway.
Sure. I think you've done brilliantly in the circumstances. Absolutely brilliantly. Oh, sorry.
I hear no questions.
No, sorry. Forgive me. I muted my microphone because there was some feedback and I didn't know whether it was coming from me. I just think you've done brilliantly. The other thing I wanted to ask you about is this complex to mag2 block. So we've got going to the fast Fourier transformation, then it goes to complex to mag2, and then goes to Ezra. So what does the complex to mag2 do?
Those blue little boxes coming out of the SDR indicate that those are complex numbers. That's what the values are being sent out as. It comes out of the RTL SDR box as a stream of complex numbers. Those are voltages in time being read from the receiver. Okay. We can collect them into vectors. That's what the next little box does. Stream of numbers into collections of vectors. That's controlled by a variable up there called vector length, kind of straight above it. And so now they're in packets of 256, I think is what we've got this thing set to at the moment. That kind of defines how many frequency buckets, frequency bins you have in your spectrum from your receiver. We're using an RTL SDR, and so 256 is a convenient number. With an air spy, you might want 1,000 or 8,000 or something big like that. Okay. You get to choose how many, what's the resolution of your frequency spectrum. Now, then it goes into the FFT box, and we take all those time voltage numbers and with remarkable math turn them into a frequency spectrum of energy, I guess. It's not, energy is a big word. I guess voltages is what they are. But what we're actually looking for is power. And so the math says that you need to find the square of all those numbers. And that's what that third box does. It takes the complex values and figures out how, takes the, let's see, the magnitude. So that's the square of the real and the square of the imaginary, and then the square root of that. It's kind of the length of the vector. And then after that, you multiply it to itself again to get the square of that length of the vector, and finally squirts out as a floating point number for each one of those freq bins in that orange pin. Is that the kind of answer you wanted?
I don't know. Do you understand it, Ted? I'm sure it's the right answer, but personally, yeah, thank you, Ted.
Perfectly understandable. Yeah, these are complex things you're asking. That's why I wanted a very simple program to make it less complex. Despera has a very fancy, interesting section for those three boxes in the middle.
Yeah.
It's probably more efficient and stuff, and you can take their stuff and plug it in the middle instead of my three boxes. But then my explanation would be even longer trying to describe what they're doing. So I'm starting with the simple, and then we can start moving these boxes around, connecting them in different ways, kind of like Lego blocks.
Well, yes. Okay. All right. Well, thank you very much.
A lot of that was changing the values in time into power spectra. And there's a bunch of math in there, in those three boxes doing that kind of stuff. Hooray that it's written in C.
Yeah. I think what you've done is quite brilliant, and thank you very much for sharing it with us. Just back to
it's thumbing attractions. This is why we care about GNU radio. That's supposed to be the key. And we're working on it.
Yeah. So before I back off from here, I'll just take back to the live spectrum, which is very effectively picking up hydrogen there. I suppose what we need to do is perhaps find some way of turning this frequency bin into actual frequencies at the bottom. Or is that already in there, Ted?
Frequency bins. Yeah, I hear what you're saying. I'm just trying to show you a warm, comforting graph to say, yeah, I guess I'm recording good data. What those frequency bins represent as far as megahertz is another issue. If I did that, it would take more time, and most of the time you're not looking at it. So why am I wasting processor time doing that, is what I'm thinking. I want a collector to be running as fast as possible to create a file, not so much display stuff. I will also make a new point. Your spectrum here has a real big, long slope coming from the top left down to the bottom right. Later on, EasyCon will take out that slope, and so I don't think I really care about the slope. I will simply trim off the extreme left and the extreme right so that it is a straight line that is sloped. And EasyCon automatically removes that slope.
Okay.
So your graph looks weird, but I don't care. Back to Andy.
Okay, thank you very much indeed. Is there anything at the moment that you would like to to say or ask about this, Dave?
Andy, perhaps you're muted.
Oh, I'm okay. Sorry. We seem to be getting some feedback at some point, and I'm never quite sure whether it's myself or not. Sorry, Dave. Anything else?
Andy, I think it may possibly be me. I've got a fan running on my laptop here. If you're hearing the feedback now, and if I turn off my microphone now.
Well, I'm not hearing it either way at the moment. It doesn't matter. It's not too severe. Don't worry about it. But is there anything else that you would like to ask Ted about this, Dave?
Not really. I just that last comment was interesting about the slope. That slope looks very, very familiar to me. As like you said, I don't worry about it because I know that EasyCon will sort that out. But yeah, that looks very familiar.
One of the issues I know that Ted and I have had when we've tried to, or when he's tried to write the SOAPy drivers to run EasyCal with USRP B210 SDR with a large bandwidth of something like 8 or 10 megahertz, is that this slope turns into a hillock on the one side, and that can make some issues with trying to remove the frequency.
Andy, on the top right, why don't you turn off the ref div or sub, whatever you have there, to off.
Yep.
And we'll see the raw spectrum. And this is the raw spectrum is the explanation for all these other funny shapes we see here. We have to let the program catch up, though.
Yeah.
Eventually, we'll see that kind of three hump of the RTL SDR spectrum. And that's more a function of the components they chose to use in the electronics. That's the frequency response of the device we're using. And it's causing all these other funny shapes later on, because we are combining this spectrum with that spectrum, and any bump in one of those spectrums causes a bump in the resultance calculation that we do. It notices changes.
I'm surprised
So
that
the
when we
program's taking a while to catch up.
I'm surprised that when we remove the reference sample, we don't seem to remove all of those bumps.
You are still collecting reference samples. Eventually, when we get this off to appear, there's no way really to speed it up. It's just taking GNU Radio a while to process and flush out the old request before we get the new setting of off requests.
And your integration quantity and his 900,000 is that to me that would it's running faster on here, but that would be quite a long time to cycle round for me on that large high number.
Yeah,
It's been getting me to drop that down recently, so which I've been trying.
I try to run my integration at around about 3.5 minutes.
Okay.
This was after. Yep.
I have been doing that. But, there we go. You've updated them.
Yeah.
Because of the top of that line is not flat, we're seeing a lot of this slope stuff. If we had a perfect receiver, that top line would be nice and flat. And so we're seeing some funny shapes later on. If you use reference samples, you get to see more of those shapes because now you got two waveforms interacting. There's a spike way over on the right. That's simply an indicator on the display that this is a reference sample. But we have to wait, I guess, 3 minutes now to get a new waveform with Andy's big integration number. 900,000 readings per sample.
Yeah. So perhaps just explain to Dave why I've opted for that. So Ted and I, it's not so much we have a disagreement, just different approaches. So he analyzes his data every day and works hard to remove stuff with bad EFI on it. And correct me if I'm wrong on this, Ted, but my understanding is you've told me that you are basically trying to get good quality data, and you're happy to do that. So therefore, the shorter the time period that there is on each sample, the less data you lose when you remove stuff with a bad EFI spike on it, because that tends to be very brief, and so therefore tends to affect only one data sample, even if it's quite short. Whereas in my long integrated samples, you would lose a whole 3.5 minutes worth of data. I, on the other hand, don't tend to analyse my data on a day-to-day basis. At least I haven't done historically because of the pressure of work in my job as a GP. Although maybe I'm retired now, I might be able to change over to doing that. Alex Pettit on the SARA forum, in a discussion that was on there, pointed out that in terms of affecting resolution of data, you could go up to about 3.5 to 4 minutes with a 1 meter sized dish without it having any radical effect on the quality of the Milky Way map that you produced at the end of it. If you had a larger dish, then it's you'd have to have a shorter integration period, but so 3.5 minutes. So in my case, what was happening is because I wasn't looking at it for up to a month, I was ending up with vast numbers of files that needed integration with EasyCon, which was taking anything up to 3 or 4 days to process on my computers, that 1 month's worth of data with a 31,000 integration quantity. So I've increased the time period to reduce the number of EasyCol data files I've got that then need to be processed. I can see that this has now changed to an antenna spectrum sample, and we can see that hydrogen has become more obvious in the middle, and that the upslurring line at the bottom right has disappeared, which is what Ted uses to indicate a reference sample on this plot. Do you want to say anything else about it, Ted?
I agree with what you're saying, and I think of it slightly differently. We collect a whole lot of samples in the beginning. How fast should we group them? We collect a whole lot of readings with our receiver, and how often should we group them into samples? And that's the integration quantity number discussion. Eventually, you want to take all those readings and represent them in your output. So eventually you want to average them, or integrate them is the bigger word, to smooth out all the noise in those readings. And somewhere in the middle, we have these intermediate results, like shown here, when we actually look at the samples themselves. If you have samples that represent a lot of readings, they look rather smooth and nice like this, and don't have much noise in them. If you have samples in the middle of all that process that have only a few readings in them, comparatively, then you have more noise. But Ezra integrates all the readings eventually. It just depends whether you want to do it in your collecting program, or whether you want to do it in your analyzing program at the end. If you have lots of samples, then you have bigger files and things like that you have to deal with. But it also gives you the opportunity to throw away samples because they don't represent much time. And so you carry on. Easy Sky does integrating of all your samples, therefore readings, and Easy Gal and Easy Glon, when you play with galactic stuff, also integrate all these samples. So eventually you do integration at the end, and you can do some integration at the very front when you collect, and you get to decide what that ratio is. I choose bigger files just because I want the answer faster. I don't like waiting around 3.5 minutes like this to see changes. And it also allows me to edit out bad data like RFI. And I know that Ezra eventually integrates all that stuff at the end anyway. So that's a higher level view of the thing. Andy.
So I think, so what I understand there is that actually, in a sense, you are preserving more detail in the data by having shorter integration times, which gives you more options later on in terms of what you do with the data, and you don't lose the advantages of being able to integrate it over longer periods anyway, because it's done in the processing software later on.
And all these intermediate results that we typically look at have more noise on them, and the files are bigger.
Yeah. Okay. That's quite interesting. The other thing that I find quite interesting about this software, and I know in some of the latest beta versions of Ezra, it's also available, but it is the, if I come down to it on here, where have we got it? You've got ANT between ref. So you can actually, I put 5 here, so what that means is that this will now take 5 antenna samples and then a reference sample. So you don't have to have it, so it just does 1 reference sample, then 1 antenna sample, which means ultimately you'd only get, you'd lose sort of half your data in a sense. But here, if you decide that 1 reference sample every 5 or every 10 or every 20 is more than adequate, then you can set it up like this within the software, which I think is great.
This has to do with how fast is your system changing. We see a variance having to do with temperature. Sometimes we see just changes. We think it may be microscopic changes in our electronics, that something shifted slightly and it isn't as conductive as it was a moment ago. We don't know where all these changes are coming from, but they happen. And so maybe we want a reference sample frequently, or maybe we don't need it that frequently, or maybe we don't need it at all. But the setting and between reference allows you to choose. Again, so many choices to be made.
Brilliant. Dave, anything more?
No, that's very, very interesting. I know that I've been having some discussions with Ted only last week, I think, about sample rates. Mr. Ted put something together for me, an easy comp to look at some of the data in a slightly different way. And I'd been using the 550,000 samples I think I got from you, Andy, because it gave nice, smooth, easy color picture. I know Ted's been encouraging me to reduce that, and I'm trying that right now, actually. Dropping it right down. But yeah, that's very, very interesting to hear that and hear the background. I understand that you don't have to worry.
So if you were going to take a picture of the stars, a long exposure gets a much cleaner, cooler picture, as long as the Earth doesn't rotate, and give you star trails. But wouldn't it be a shame if you were taking a remarkable picture of a nice long exposure of the Andromeda Galaxy, and then a satellite flew through your view? It'd be nice to take that period of time that the satellite flew through your image and remove that. And of course, digital processing allows you to take lots and lots and lots and lots of images and then stack them all together. That's called integrating. And remove the things that you don't like, the blurry images or when a satellite flies through. And it's the same concept with Ezra here. Do you want to take lots and lots and lots of images and integrate them later? Or do you want big, long, 10-minute exposures that gives gorgeous images, but they might be blurred because of the Earth rotation? Same problem here. But we have small dishes, so it's hard to have a blur. But if we had RFI or a satellite come through, it's a bummer because it removes a whole lot of your readings are no good because they're all assembled together.
Yeah.
Long exposures or short exposures. Same thing in optical.
Yeah. Yeah. Thanks for that, Ted. That's a very good analogy and makes a lot more sense now.
So how does, in terms of gain on this, Ted, on the RTL SDR source, you've got an RF gain of 49, which I think is the highest gain. In Ezra Sync, you've got gain string of gain space XXX. So how does that define gain within the Ezra Sync, and what does gain there mean?
In my Ezra Sync, it simply is the string that gets written to the file. Historically in the file, I wrote what the gain was. Right now in Ezra Sync, I have no way to figure out what that is. I haven't gone to the trouble. It's kind of a low priority in any case. And so I have provided a way to put a string in the file. If you want to provide that string with a different characters and write in the gain, go ahead. But I don't know what the gain is, so I put XXX. So it's more just to be compatible or look like the historical file.
Okay, so gain isn't just the 49 that's on the RTL SDR source.
My Ezra sync has no idea what the gain is and can't change it. So it writes a string out to the file with X's in it.
All right, okay. The other thing...
if you make that a single quote, I think it will put out a £sign with nothing else on the line. So, in any case, it's a comment.
Right, okay. So, the other one thing, I don't know if you've found a way of doing this yet, you may not have done, or maybe there isn't a way of doing it, is in many software programs such as SDR Sharp, you get to choose between your software-defined radios with a drop-down menu. So, well, I have an SDR, RTL SDR, or I'll have a USRP, or I'll have an AirSpy. But when I'm compiling one of these GNU radio scripts, it seems to check whether I have a relevant software-defined radio, and if not, it will register an error and not run the flow chart. So, is there a way of doing that in GNU Radio where you can have a selection of SDR source blocks, and then have perhaps a GUI chooser to choose which one you're going to use, and as long as you've only got one of them plugged in, it still works, do you know? Or is that not something you've got as far as trying yet?
Your question is it possible? And I say yes, but I haven't any idea how to do it, and I haven't done it. I say that because there are pretty there are attractive and pretty uses of GNU Radio to provide you a pretty receiver application.
Right.
And I even forget what it's called, but anyway, it is underneath it. It's using GNU Radio, and it provides this drop-down menu and stuff. SDR Sharp doesn't use it, but there are other ones that do. And so somebody figured it out, but I haven't made my program that complex yet. Let's get the thing to work at all, and then we can put all these ruffles around it. In fact, we probably could hide GNU Radio entirely and have it more like just an application that runs. And that's a possibility. But we're not there yet. We are on the frontier, you can see, learning a lot of stuff along the way.
Okay, no, I appreciate you explaining that. Thank you very much. Okay then, so I'm going to stop sharing on this for the moment. Go back to our main screen. And so the second part of our evening tonight was just to look at the homework from the last meeting. So I'm sure you, well, I know because you've all done homework. So at the last meeting, to remind people, we're following our process using our textbook, which I'll just show people again. A brilliant book in my mind. I just emphasise that none of us here have anything to do with the publication of this book. We didn't write it. We don't get anything out of it. It's just what we're using for the course, which is Practical SDR by David Clark and Paul Clark, which is really all about using GNU Radio with software-defined radios, and walking us all through from the basics. So at the end of the last meeting, we agreed we'll all have a go at a bit of homework, which involved choosing to do one or both of either creating our own AM radio or creating a script that would allow us to play chords, basically musical chords, and choose between a number of chords. This is not meant to be anything to stress people up. It's meant to be just a bit of fun. And it doesn't matter whether what you've produced is any good or not. It's just us trying to see if we can just produce something and play around with some of the ideas that are in the last meeting. So, who fancies going first? Dave, Ted, Dave, do you fancy going first?
Yeah, I'll go first. Yeah, why not?
I got to say,
Might as
I do have an example from Andrew Satowski as well, which he was it got a video of what he did for, which he's happy for me to play at the end. So there'll be 4 of us.
Okay. So I just did the AM radio. I didn't do the chords one because at the time I was having trouble with my sound card. I think my SDR was just producing a horrible noise. I think I now know what the problem is, but anyway, never mind. I did the transmitter one. I have to say, Andy, I found the exercise extremely useful.
Right.
Just to I don't know if it's just put people off. Maybe that's why there's not many people here this week, but I think it didn't. But anyway, I found going through the exercise of having to do it very, very useful and interesting, and making me think and go back and spend a lot of time, looking at YouTube in the background and trying to think about it. So it was a very, very worthwhile thing to do, I have to say.
Can I just say that I did do the chord selector, and as you'll see in a few minutes, my computer was also producing really awful sounds out of the sound card, and I don't think that's got anything to do with the computer. I think it might be the flow chart. And me being tone deaf.
Well, mine was really horrible, but anyway, yeah, okay. So I did the AM radio thing. So I'll share my screens. Hopefully this will work. Okay. You can see that, and I'm hoping you can see the other little drop down window too.
At the moment, you're not sharing your screen. You'll need to. Yeah,
screen 2. There we go. Are you seeing? I can press allow.
Yes,
hopefully
we are
you're
now.
seeing my. Yeah, brilliant. Okay, so there we go. So this is it. I did do the audio source extension bit. I did that in. So I've got my carrier signal, audio source with a constant, which I can tweak around with, multiplied it, put a throttle in. I didn't put the throttle in to begin with. Found my fan, the computer fan was just going absolutely crazy. Till I read about throttles, put that in. That calmed things down no end. And then put in the time sync with some a number of connections so I could see the individual parts, and the multiplied signal together with the frequency sync. And this is the result, which let's see, we've got this running here. So here we go. So this is me talking right now. Let's flip through. So I've got turn everything off. So I've got a carrier which I can tweak around with my slider here. Played around with that. Yeah, okay. There's this is the signal source, which is coming in from my microphone, which you can see here, and then the modulated signal, which I suppose is what would go to be transmitted, is shown in blue. So there you go. That's it really. And down here we've got the frequency sync, which spend a bit of time reading about what I'm seeing here.
Oh, I'm incredibly impressed.
That's it.
Well, what's all these buttons you've got on the right side that says axes?
Oh, over here.
Yeah.
Oh, I found out about a control panel that you can bring up. See, middle. I think it's middle button, isn't it? If you bring up the middle button, you've got all these things you can muck around with, and the bottom one's a control panel. So you can muck around with scales, and you can turn it off too as well. You can freeze it, which is very useful. It was doing my head in having this thing going in all the time on the screen. Yeah.
Oh.
There we go.
Is that how you got the 3 little buttons, modulated, carrier, and signal source, to appear as well?
Yeah, that's right. And you can turn things on and off. That's everything all at once. But of course, you don't want to see the carrier, do you? Because it's boring. It's always the same. They shouldn't play around with it. And you might not want to see these signal source. You might just want to see the modulated output. I can just turn these on and off.
So you just right-click on the.
Oh no, actually, no. This didn't. These three didn't come from that.
Oh no.
Gosh, my goodness. Can't remember how I did it now. Don't know. Anyway, it's very easy.
3 inputs into the display. And I
Yeah.
think you turn
Oh, that's
one
right. You
on
get it
and
off here, don't you, Ted? You do it over. I think you do it over here. Was it on? I don't know. It was somewhere. It was somewhere over there. It wasn't that difficult.
They actually may just show up.
Yeah.
As if like maximum hold and minimum hold and stuff we had before. But you have 3 inputs now. What are your inputs? Yeah. Or maybe that's a setting. I'm kind of fascinated by your spectrum frequency on the bottom.
Oh, right.
It's kind of interesting that there's a negative kilohertz, but that's indeed math work on the converting the voltages into frequency with the FFT function. And so you get this negative frequency numbers as well. That's just how the math works out. But it should be a mirror image right around the 0. So you're changing the frequency up and down. And so if we only look at the right half, that's the way we commonly think of it, from 0 up to positive frequency. And I think there's probably a way to show just the absolute value of it, and therefore remove the left. What's kind of fun is I think if you talk in a low tone with your voice, that only the middle section near 0 will light up.
Okay, let's just have a go like that, something like that.
As opposed to a high pitched voice.
I'm trying to talk with a low pitched voice, Ted.
I don't know.
At one
Maybe
stage,
it's all low. That's only kilohertz. So yeah, maybe the high pitched stuff is way off to the right. We don't even see it. Anyway, that's fun to see the control panel. I wasn't aware of that either. Great work.
Oh, okay. This all comes from watching YouTube's, Ted, and people just tell you things, don't they? And you think, oh, that's interesting. Let's try that.
That's why we show up at these meetings. Yeah.
Yeah, that's right. One thing I did have working, and it doesn't seem to be at the moment, is by mucking around with the constant, I was able to shift the signal source up and down. I was able to get rid of the negative side, so it would clip it off. And it's not working at the moment, and I'm not quite sure why. Not working at the moment. But in an earlier version of this, I did have I had shifted everything with the signal up, so I didn't have I only have one side, the positive side of the carrier working, so I only had one peak down here. But it's not working at the moment. Anyway, that's it. That's me. So better move on.
Oh, quite brilliant. Thank you very much for showing that. It's very good. Very good. Ted, would you like us to show us yours, or would you be happy to go next?
It'll be really quick. I'm busy on other things and I haven't done your homework. I'm sorry, teacher. I apologize profusely. Here's an apple.
It doesn't matter. It's only meant to give people a chance to try things out. As Dave said, it's just an opportunity to learn how to use it. And I think if there's one person of the three of us that doesn't need to practice, it's probably yourself. But do you have something to show? It doesn't matter if you don't.
I have nothing to show.
Fair enough. That's no problems at all.
I haven't read the assignment. That's where we are.
That's actually fine. It's as I say, it does not matter. This is not meant to be some exam. Okay, I will have a little show of what I've done then. So, okay, so let's get rid of that. And somewhere. Okay, well, I have a problem that if I play GNU radio scripts on this computer, it stops the sound being recorded on the screen recorder for the YouTube channel. So what I've done is I've gone through it in advance and created a little video of it, which I can speak to as we go along. So this is. What I'm going to do is talk about the main one, which I had some fun looking at, which was the chord selector. So I had a. Oh, I wonder if we get rid of that feedback a little bit. But perhaps Dave, you could try muting. See if okay. Oh, that seems to have worked very well. Yeah. So I'll just take this back. So you can see that my approach to this was. Just to try, because the idea was to have at least 3 different chords, and to try and to choose between those and both play them and display them on the screen. So I created 3 multiples of. Just remember how I did it now. This is so this is 3 different frequencies which were a chord. I think we started with the C chord, didn't we? And then I've got a frequency sync to show what it's like before multiplication, and I've got, I think, pull this up. Hang on. Oh, I can't show it. Wait, hang on. We'll see in a second now. Just play it. Is it playing? It's not playing now. Great. Okay. Oops. I do apologise. Okay, you can see I looked up how the chords varied from each other, so it may not be an accurate description of how chords differed. And in the frequency for each of the signal source ones, I added in a multiplication factor, which was meant to choose between chords. That was the idea. You can see I've done it on each of the 3 blocks. That's what this is showing. And then in that's the frequency sync block, which seem to have lost. Maybe I can go back slightly. So this is using an FFT of 1024 and a sample rate which I can change. I forget what the advantage of that was. Because I set the sample rate at 32k for everything anyway. And again, there's so I've created a GUI to put in a chord selector to just choose between the chords. So here we are. This is just showing it in action, and I'm now going to try changing the chords. Well, it's show you the different choices. First of all, so it's showing you the 3 frequencies individually at the bottom, how they combine together to a single graph. And here I've gone and changed it to the next chord up. And now I'm changing it to the next chord up. The sound seems to take a few seconds to catch up. Again,
Andy, I'm not hearing any sound.
Oh, are you not?
I can hear you, but no, but not from the
oh, really? Oh, not. Are you hearing anything, Ted?
have heard no sounds. We see pictures, which
Ah.
is close enough.
I don't know how to do that, but you saw that the. It's a shame about that.
It could be the Teams is removing background noises, and it thinks that's a background noise.
Yeah, I'm sorry, but you saw the graphs moving across, didn't you? And the amplitude was changing as well as the chords went up. I apologise that the sound wasn't there. Anyway, basically that's my method for doing it. And as I said, also I've got one from Andrew Stowski as well. Is there anything you'd like to ask me first of all before I show Andrew's? No, so I'll show Andrew's. Now this one actually is another video, but it's also muted, so you're not going to hear any sound on this anyway, so it doesn't really matter. It's basically for me to speak to as it goes along, just to show what he did. So he came up with a much simpler method for doing it, which, like yourself, had a single additive bag block in the middle, and for the 3 different signal sources for the different chords. So he's showing that you can magnify a particular part of the graph very easily. As you can see, he's set it up so that you can actually then just change the individual frequencies as you go. So rather than having sort of 3 buttons to 3 chords, you just put in the frequencies that you want. Okay. So I don't know what thoughts you guys have on those approaches.
Yeah, thanks, Andrew. Pretty good.
Well, it was a bit of fun, and as you say, playing around with the different blocks and trying to create something for yourself.
As I say, very worthwhile exercise. I mean, mine's probably spent about 4 or 5 hours on it, trying to do it. but it was very worthwhile doing. Yeah.
It was taking me about 4 or 5 hours just creating those GUI inputs for Ted's Ezra G harp. So you obviously work faster than me. Okay, guys. Well, we're reaching 9 o'clock now, which is the sort of formal end of the meeting. So thank you very much indeed for taking part today. Sorry, there's only 3 of us, but I hope you found it was fun. So in terms of another meeting date, do you still think Saturday works well, or do you think it's better to try and move to a different day of the week?
And yeah, Saturday's absolutely fine for me. I worry about other people though. You know, if there's only numbers have dropped off, is that because of Saturdays? I don't know. But you won't be able to find out, will you? Really, without asking people.
Well, I can. So rather than setting a date today, I could send a message out to members and ask them whether a different day of the week would be better for them.
Yeah. Okay. I have to say, I found today's meeting exceptionally interesting, actually, with seeing Ted's work going on, and I don't know if the meeting diverged a bit from the topic. I suppose it didn't really. It was all GNU radio, wasn't it? But bringing in the Ezra aspect as well, I found it exceptionally interesting.
Well, I think it was a good discussion of how you could take an existing process, in this case the Easy Cull process, and convert it into a GNU radio version, and what happens outside of the process that you're trying to replicate is also very relevant. In this case, Ted's discussion there of integration, quantity numbers, and how that actually related to further programs in the Ezra chain, such as EasyCon and EasyCal, etc. So I think that's very helpful indeed. And thank you very much, Ted, for that. We very much appreciated that. It's very kind of you.